there are two major types. The first one is called phase controlled AC voltage controllers. So now we will start with the phase controlled. The first one in the phase controlled is half wave semi-controlled AC voltage controller circuit with resistive load. So in your studies, we are talking about the R load, RL load, E load. It means you are charging the battery. E means energy, or the combination of R and E or RLE. So we are studying this. Why do we study this? Because in each application, it has a different property. So for example, in your laptop, you have the energy or the battery you are charging. It has some also resistive combination. So this R and E combination, the load has. So we need to study mathematically like how the circuit is working when you change the phase angle and how long it will take to charge the battery and so on. I'm talking about AC to DC, but this AC to AC and in all converter circuits, we have to apply different load and study about the circuit before we use that in the practical applications. So in this example, we are going to study only this half wave circuit with the resistive load or R load. And this is the circuit. The circuit construction is very simple. So you have one SCR, it's connected towards this direction, anode, cathode, and then this anti-parallel is diode. So diode is connected in this direction. So that is why we call this as a anti-parallel pair. Okay, so and I apply the input voltage and then I get the output. The output current is flowing through this resistor. So the load is the resistor. So now we will study about this circuit. You already know how this ACR is working. So whenever you apply the gate voltage, the ACR, and also you give the forward bias, it means you are giving plus and minus, plus to anode, minus to cathode, and you apply the trigger signal or the firing angle to the gate. Then this ACR will go to the forward conduction mode. So last week, I think I told you, if you apply the negative voltage to this anode and then the positive voltage to cathode, then this ACR will be in the reverse biasing. So that is called reverse blocking mode. And similarly, you keep this one as a positive and negative forward bias. But if you do not apply the trigger signal, then this will be in the forward blocking mode. So forward blocking mode, forward conduction mode, reverse blocking mode. These are the three basic operations of this SCR. So right now, let us assume this one is in the forward conduction mode. It means I apply the correct voltage here, positive and negative here, and then I also apply the gate voltage. So now this is conducting. So this is happening during the positive half cycle of the input voltage. So the input voltage is the sinusoidal. So here you can see this is the input voltage. So the positive half, during the positive half cycle, this will be plus and this will be minus, then this is conducting, no problem. So by changing the phase angle, I can change the delay. So based on the delay, for example, I can start the conduction from here. If I put the alpha here, then I can change the conduction from here. So the pulse width, so this is the pulse width. The pulse width will get changed. Okay, so this is the SCR. This is for the positive half cycle. And for the negative half cycle, this one will not conduct because this will be in the reverse bias or reverse blocking mode, because it will be minus here and it will be plus here. But at the same time, you are applying the minus here and plus here. So it means this one will be in the forward bias. So the negative half cycle will pass through the load and then it will come to the source. So always in the electrical circuit or in the electrical world, the current, wherever it starts from the source, it needs to come back to the same source through some path. Then only this is the complete circuit or the closed loop. If you have some kind of switch, if you open this, then the current will not flow. And if you don't have a load, then the current will not flow. So, and if, for example, if you do not apply the gate voltage and this is in the reverse bias, it means this is in the open circuit. So the current cannot flow through this path. So always the current is starting from somewhere and then going through some path and then coming back to the same source. Then only it will fulfill the complete cycle. So now the positive half cycle is okay. The negative half cycle is okay through this diode. Here, why we call this as a half wave? So because we can control half wave, we can control the positive half cycle by delay angle, but the diode means we don't have any external terminal, only two terminals, anode and cathode. So it will conduct the whole negative cycle. So for example, this is conducting the whole negative cycle, the complete negative cycle, but the positive half cycle we can control. That is why we call this a half wave. I told you here, half wave semi-controlled. So half wave semi-controlled, we can control half. So this is a AC voltage controller. So you have the control only between 0 degree to 180 degree or 0 to pi. So you can change the alpha value between this angle. So here you can just read by having a control on the firing angle alpha, the load voltage may be controlled, of course, by changing this pulse width. But finally, if you make the average at the output, it's going to be different. Our goal is, what is our goal? Phase controlled AC voltage controller. By controlling the phase angle, we are changing the AC voltage magnitude at the output or amplitude at the output. So this is the first one. And so here some equations. VO RMS, again, we have to find the VO RMS output voltage, RMS value of the output voltage. RMS means, I explained last week how to calculate the RMS, root mean square. So we are making the average of all the cycles, whatever we are applying. For example, when we apply 230 volt 50 hertz, 230 volt 50 hertz, it means 50 cycles are passing through per second. So we need to find, now we are studying only about one cycle. So we need to make the average, then we are using the integral, and of course we are using this square root, and then we are squaring also the input voltage. So that is the standard formula we have to use. Root mean square value of the output voltage is equal to, here the limit is, we are always using this one cycle as the reference. So 1 divided by 2 pi. So this is a 0 and this is the 2 pi, one cycle. So 1 divided by 2 pi, integral of alpha to 2 pi, because we are starting the conduction only from alpha until 2 pi, one cycle. And the apply voltage is Vm sine omega t. So here this is the supply voltage. So we are squaring that, Vm square sine square omega t d omega t, the whole power 1 by 2. This is just to represent the square root. So you can just simplify this equation, same like what I said last week. So Vm square, when you take out from the square root, it will become Vm, and this 2 pi will be square root of 2 pi. And then this equation will be like this. And of course, sine square omega t, you can rewrite like this, 1 minus cos 2 omega t divided by 2. And then you can further simplify this equation. So you can apply, of course, first of all, you have to do this integration. So constant, when you integrate the constant, then it will become omega t. With respect to omega t, we are integrating. So omega t minus cos will become sine. So sine 2 omega t divided by 2. And you are applying the same limit, alpha to 2 pi. And when you apply the 2 pi and alpha, then it will become like this. So 2 pi minus alpha, and then plus sine 2, because instead of omega t, you are applying these limits. So this is the standard limitation you are applying in the mathematics. And you will get this final VO RMS. This is the final formula for the RMS value of the output voltage of this circuit. And IO RMS is equal to V divided by R, I equal to V divided by R. So simple Ohm's law. So IO RMS, it means output RMS value of the output current is equal to VO RMS divided by R. VO RMS already, if you find here, then you can just use this formula divided by this resistor value. And input power factor is equal to load power divided by source VA. This is also the same. VO RMS, IO RMS, VO RMS, IO RMS divided by VS, IS, the source. And then you can, this input current is equal to output current. So you can cancel this. And this is the actual formula for the input power factor. And similarly, conduction time of the thyristor. Thyristor means what? That is the SCR. So conduction time of the thyristor, T is equal to pi minus alpha. So because you are conducting only from here to here, so pi minus alpha, if it's 180 degree and this is 30 degree, so 180 minus 30 degree. So pi minus alpha divided by omega. Omega is the 2 pi f, right? That is the always the standard formula for omega, 2 pi f. So this is with respect to the input frequency and one cycle angle 360 degree. Okay, and similarly conduction time of the diode. Diode means it conducts the entire half cycle. So it means 2 pi minus pi. This is the 2 pi and this is the pi divided by omega. So 2 pi minus pi is equal to pi by omega. This is the formula for conduction time of diode. And this is the formula for conduction time of thyristor or SCR. So now we had seen this first circuit. Let's move on now. So you see here, I write the formula like this, but in some books, they rewrite the formula in this way. It means they keep this pi inside the square root, the same. So both formulas are the same. So don't get confused. So that's why I had given this reference as well. So in some books, you can see this formula. So other than that, everything else is the same.